let's cover the second fundamental theorem of calculus. And if I could sum it up really quickly, what we're going to learn to do is how to take the derivative of the integration of a function, which might seem pretty straightforward in that it would almost cancel itself out, but it doesn't quite work that way. And the other issue is that the integration in these cases, at least in these examples we're going to do, would be using variables other than the variable that the original function has. So, for example, take a look at these 4 examples on the bottom left-hand side of the screen here. And I'd actually like you to take a minute and integrate these 4 similar, well, the functions are the same, but 4 similar integrals. So do these 4 definite integrals. Don't forget the first fundamental theorem of calculus, which means you're going to, for example, in the first one, plug in x and then plug in 0 after you integrate it and subtract the 2. So go ahead, do these 4 problems. Pause the video, do these 4 problems on paper. Doing the definite integral, it's the first fundamental theorem of calculus. Plug in the x, plug in the 0, subtract the 2. For the second one, plug in x, plug in 2, subtract the 2, and get the final result. Okay, so do that now. Okay, hopefully you've done that. Lloyd, I know you didn't do it, so stop, pause the video, do it again. Okay. Now I hope everyone's done it. So let's take a look at this first one. Now, to make our lives easy, right, I'll show you this in 2 seconds. We're going to raise the power by 1 and then divide by that new power. And I put a 3 here. I wanted this to reduce really nicely. So we're going to get t to the third for each of these problems, okay? Because that's not really what the focus is. So to make our lives easier, I made a very simple problem. So I'm not going to show that work that I just did because I hope that's nothing new to you. So I'm just going to write the result just to save a little space, okay? So when we integrate that, as you just saw, we get t to the third, okay? When you integrate 3t squared with respect to t, right? That's why I know we're going to do the reverse power rule here for t. I get t to the third. Okay, don't forget, we're going to evaluate that. This is a definite integral. It's not plus c, for example, which you're used to doing. We're going to evaluate it from x to 0, which just means that's the first fundamental theorem of calculus. We're going to plug x in, plug 0 in, and subtract the 2, right? So when I do that, I'm going to get x to the third, right? I'm plugging x in for t. Let's make that perfectly clear. I'm plugging in x for the variable for t. Usually you're used to have a number here like 7 or 1 or 2. So if it was 2, you'd get 8 minus 0 is 8. But we can plug a variable in also for t, and that's what we're going to do today. We're going to plug in x. Okay? So you get x to the third, and then minus plug 0 in for t. You get 0 to the third, which is nothing fancy. It's just x to the third. You don't normally put a plus 0 here. I'm going to leave it there, though, for purposes you'll see in a few seconds, I hope. All right, let's do the second one. So the second one would be t to the third, evaluated this time from 2 to x, not 0 to x. Other than that, it's exactly the same. And that would be x to the third, like we had before, minus 2 to the third, which is 8. Okay, and I really don't need to write it twice, but I will. X to the third, sorry about that. Minus 8. Okay, the third one. This would still be t to the third, but now we're going to plug in a 2 and a 2x. Okay, so what happens when I plug in a 2x is I'm going to get 2x to the third, right? And believe it or not, I'm going to leave it like this. Of course, you could get 8x cubed and write 8x cubed, which you probably did. Minus 8. Okay. But I'm going to leave it like this on purpose because we're going to show you what happens in a second when we take the derivative of it. And it's easier to see the result of that by leaving it like that. And the last one, t to the third, evaluated from 2 to 3x instead of 2x. And again, just to compare them, we're going to get 3x here to the third minus 8 equals, well, same thing. Okay. Nothing surprising here. Okay. All right. Now, what I told you we were trying to do is we're trying to answer this question. So, and we're going to see this a lot on the AP exam. If I want to take the derivative with respect to x of, right, of something, and that something and I'll take one of these, for example. I'm going to take this guy. Actually, we'll do this one. We'll do this one because this is going to be the toughest one of all. So I'm going to copy and paste it. Okay, we want to see, we want to see what happens. So this is what the second fundamental theorem of calculus is going to tell me. What happens when I take the derivative with respect to x of an integral from 2 to some x value? That's really important. These two have to be the same here. Okay. Of some function. Now this function, the variable doesn't matter that it's t. It could be w, it could be s, whatever. Because after we integrate it, we're going to plug a 2x in as we just did below. Okay. So I'm trying to figure out what would happen if I did this. Is there a quick way to do this rather than all of this drudgery work that we're doing? And there is, and we're going to talk about it in a few seconds. So what we're going to do now is we're going to do that. So I'm going to use blue to show you. So I'm going to take our expression here that we just found, and I'm going to d dx this expression x to the third plus 0. Okay, and let's see what we get. And the derivative is, of course, 3x squared plus 0, right? Plus 0 because this is a constant. And let's do it for the next one too. So let's take the derivative with respect to x of x to the third minus 8. Now look what happens, right? We get, let's put that plus 0 here, even though we normally wouldn't write it, right? We get 3x squared, and the derivative of negative 8 with respect to x is 0. Okay. And now let's take the derivative of this guy and watch what happens, right? Actually, I might take a quick break and just talk about a couple of things up here, right? Let's talk about a couple of things that happened over here before we go on. So notice that this answer and this answer is exactly the same, right? Because this 8 doesn't matter, which means way back in this problem, if this is a constant, we really don't care what the number is. It did make a difference for the derivative. I mean, for the integration, excuse me. It did make a difference for this integration. But once I took the derivative of that integration result, it didn't matter. See, they're both 0 here. So you can see that a 0 or a 2 in our final analysis here is going to make no difference. See, this number down here makes no difference in our final result. This could be 2, 8, 17, 3, 1.4. It doesn't make any difference at all because when we integrate it, it becomes an integer, but when we take the derivative of it right after that, the derivative of an integer is 0, so it makes no difference. So that solves one mystery. But let's see what happens now when x is more c. So now we're dealing with this. See, this was x, and that seemed to work out just fine. But what happens with 2x? So let's see what happens when that's anything but x. So let's take this derivative. Notice I left it in this form on purpose because I want to see what happens as a result of the chain rule. There's going to be a chain rule going on here. So look what happens. We get 3, move the coefficient in front, times, leave the inside alone, 2x, drop the power by 2. But then don't forget, times the derivative of this, right? The inside. That's what the chain rule says, right? So times, I'm going to put it in red here, times 2. And as we know from before, this 8, right, this minus 8, the derivative of that is just plus 0. So we, again, just like all of these here, these are all 0. Same thing happens, okay? But something else happened, right? We had that red 2. So let me just do one more, which again, hopefully you did, or you will do. And let's see what happens when we take the derivative of these guys, right? So the only difference between this and the one above it is a 3x instead of a 2x, right? Okay, so the derivative of that, right, is 3, leave the inside alone, drop the power to 2, times the derivative of the inside, right? Chain rule, times 3. And again, this is plus 0 or minus 0 because of this negative 8 here. All right, so let's see what happens, right? Take my highlighter here. And let's see what happens. When you take the derivative of this function, it really ends up to be the same function almost. Take a look. So this is 3t squared. This came out to be 3x squared. So in a way, almost taking the derivative of an integral, in a sense, kind of cancels it out, right? But not quite, not really. So a couple of things happened. First of all, the 2x, right? Well, in this case, the 2x. So let's take a look. Not this one, this one. The x gets simply put into the t, right? So right here, when if I was to put it in front here. So if I was to take derivative of this with respect to x, which is what happened at the very end here, right? Basically, all that happens is this x gets put into this t, and you can see it right here, 3x squared. Right? The x replaced the t, no problem. Here, if I was to do this one, right? This x gets plugged into the t. Notice the only difference is 0 and 2. That made no difference whatsoever. You still get the same answer, right? So the x just replaces the t. But here, that doesn't happen exactly, right? This 2x, if I was to dx this, take the derivative with respect to x of this whole integral, I do plug the 2x in where the t is. You'll see it right here. There it is, see? I do plug the 2x in where the t was. This used to be 3t squared. Now it's 2x squared. Just like here, it was 3x. See, so I still plug it in. And even this last one here, I plug in a 3x, see? So this 3x gets plugged into the t, okay? So all of this is true. There's just one small thing. I hope you see it. It's in red, of course. There's one small issue, right? If this, right, if this has a derivative of anything but 1, right, so the derivative of this blue here is 2, the derivative of this is 3, we have to multiply it by that number. So first we plug it in, right, we plug it in where t is. In other words, what you're saying to yourself is, well, if I integrate 3t squared and then I take the derivative of 3t squared, although it's not really the derivative of 3t squared because there's an x in there, but if I have a function that gets an integral and then the derivative, you think, well, you're going to get the same answer. 3x squared, 3t squared, right? 3x squared over here, 3t squared, right? Over here, 3t squared, 3x squared. And it almost works that way, right? It almost works that this variable just gets inserted in here. But you have to take into account the chain rule over here in red, in the bottom right here, if it's something besides x. See, these two are x, but this guy down, these two is 2x and 3x. So all you have to do is plug that variable in and then multiply by the derivative of it. So the chain rule here, okay? So we already did this problem. This problem here is the third one. If this is problem 1, this is problem 2, this is problem 3, this is problem 4, okay? All right. I'm actually going to erase this because, right, that's not what we're doing. I'm just showing you that really quick, but that's not really what's happening here yet, right? That happens down here, right? So this is where we took the derivative of the integral. This is the integral with an x plugged in. But what happens down here, see this one? This is what we're going to do up here. So if someone says, do you take the derivative with respect to x, or really any variable, this could be u, as long as it's integrated from an integer to 2u, for example, or u, or something like that. Okay? So if you take the derivative with respect to a variable and you integrate by plugging in from an integer to that variable, okay, into any equation. This could be t or w or whatever it happens to be, right, as long as this dt matches there. All you do is you rewrite the function, right? All you do is you rewrite the function. See, what I just wrote, 3 blank squared is 3t squared, right? So I rewrite the function, 3t squared, 3t squared. But t, of course, is going to get this. I'm going to take my variable that I'm going to put it in here, and I'm going to plug it in. Okay? And this 2 doesn't matter, right? This 2 doesn't matter because when you integrate and plug a 2 in, you get a numerical answer. And when you take the derivative of numerical answer, integer, or non-integer even, a real number, take the derivative, it'll just make it go away, right? The derivative is 0. So this 2 doesn't matter. What is this? 2, 3, 7, pi. This could be pi. This could be 8. We don't care. Doesn't matter, right? Doesn't matter what this is. This has to replace the t. There it is, 3t squared. So now it's 2x squared. Excuse me. And always, and this is the only hard part, is remember to multiply by the derivative of this 2x. So it's times 2. You'll see that what I just wrote here, we're going to simplify it in a second, but basically what I wrote here is exactly what you see here, doing it the long way, right? So problem 3 here, we integrated this thing, we plugged in 2x, we plugged in 2, we got the minus 8, here it is, it's all down here. Then we took, right here, we took the derivative of it with respect to x once we were done. And you see we basically got back to the same function, right? 3 something squared, but we had this little chain rule thing happening at the end here, is plus 2. All right, times 2, excuse me, okay? And that's exactly what you get here, see? So the second fundamental theorem of calculus just says if you take the derivative of this with respect to x from a number to 2x of some function, just take that function, replace its variable, in this case t, with the 2x, and multiply by the derivative of the variable you substituted in this 2x, okay? So the final answer would look like this, of course. All I did there was multiply the 3 by the 2, okay? And then that would just be 6 times 4x squared, right? Which is equal to 24x squared. So, you know, you want to simplify the final answer, but I kept it unsimplified just so you could see the procedure for finding it, okay? So for this question, it's really question 3, or would have been question 3, that if I take the derivative of this integral, that's what I get. But don't forget, it's really just this, right? Think of it like this, and the rest of my work here is just simplification. Okay, finally, I'd like you to try these 3 problems, my class. So copy these into your notes. They're pretty straightforward. Don't forget the chain rule. Don't forget when I taught you about the second fundamental theorem of calculus. There's actually a little bit more to it, which we'll cover in class, but I want to just do these versions where it's the integral from a number to a variable. And then I want you to do the question 3 here, just A and B. Okay, A is a review, but B involves the second fundamental theorem of calculus. And it's an actual AP question. So I want you to do 1, 2, and the A and B of 3, and we'll go over those in class tomorrow.